Hi everyone. Now we are going to discuss about the silicon semiconductor. It is a case study based discussion. So what we are going to see now. So silicon semiconductor, how the silicon semiconductors are used in engineering field, that we are going to discuss it now. So core objective of this case study is analyze the diamond cubic lattice structure and its significance, then evaluate the Joukowski process for growing high purity single crystal silicon ingots, investigate the role of point, line, and surface defects in alternating semiconductor behavior, and synthesis how physical properties translate into real world applications like IC. ICs are semiconducting materials are used in integrated circuits. So that we are going to discuss now, and project the future scope of silicon in fields like quantum computing and nanotechnology. So first is diamond cubic structure. Its lattice constant is 5.43 Armstrong and it providing high structural densities. Its coordination number is 4. Its packing factor is 34 percentage. So atoms are 34 percentages only. It is fully filled and remaining space is only empty space. And its bonding type is purely covalent bond, and this provide a high melting point and mechanical rigidity required for water processing. So it's bonding, the only reason for this is covalent bonding. This bonding provides the melting point, high melting point, mechanical rigidity. That rigidity is required for water processing. Joukowski process. So perfect crystal, how can we grow? So first step is seeding the crystal. So a small seed crystal with a specific orientation is dipped into the melt, and pulling. Second process is called pulling. The seed is slowly rotated and pulled upward, showing the melt to freeze onto the seed. And the third process is wafering. The ingot is then sliced using diamond dipped sauce into the wafers, typically 20 millimeter or a 200 millimeter or a 300 millimeter in diameter, which serves as the substrate for ICs. And ingot formation, this creates a large size of crystal structure. Key physical and thermal properties. So physical properties first we are going to see. So crystal structure is diamond cubic structure. Its lattice constant is 5.43 Armstrong and its band gap is 1.12 electron volt, and this band gap is indirect band gap. Its melting point is 1414 degree Celsius and its density is 2.33 gram per centimeter cubic, and its thermal conductivity is 149 W bar mk. Analysis. So linking crystal quality to device efficiency. So this is very important. Scaling process. So enable scaling transistor down to the down to 5 nanometer and 3 nanometer nodes for mobile process. Doping control. Controlling point defect enables precious doping profiles to for advanced chip architecture. And CZ purity level, CZ process reaches 99 purity, increasing functional chip yields and crystal perfection. Single crystal dislocation is dislocation in microprocess. It causes small bit error, that's all. And its future scope is definitely it will play in many of the engineering fields as quantum computing, flexible electronics, nanotechnology, silicon photonics, heterogeneous internet. So quantum computing utilizing silicon spins as cubes for scalable quantum process, then ultra thin flexible silicon members for wearable medical sensors. Flexible electronics is used in sensor field, then nanotechnology, silicon nanowires and quantum dots for next gen light emitting devices, silicon photonics, optical communication on a chip to eliminate data eliminate data, and silicon with the 2D material like graphene to enhance electron mobility. So the foundation of solids, understanding periodically and order. So periodic ordered structure they have. The crystal physics focused on this arrangement to different crystalline solids for amorphous materials. So repetition. Geometric repetition means a single unit cell continuously repeated and form a perfect crystal structure. So this is geometric repetition in crystal solids like a silicon and atoms follow a strict geometric pattern rather than being randomly placed. And microscopic engineering, this trials such as thermal conductivity and electrical resistance are direct consequence of microscopic order. Then electronics application, it is vast applications it have. Next, broad engineering applications, integrated, it is used in integrated circuits, the heart of microprocessor and memory chips. And solar photovoltaics, high purity silicon wafers capture photons and generate clean electricity. Then MEMS sensor used in accelerometer and gyroscopic for smartphones and automotive safe systems. Power electronics, transistor that manage high voltage electricity in electric vehicle and industrial grids. Then it is also used in opto electronics also. Then they are used in tunable conductivity, then oxide formation, thermal stability, cost effectiveness, because this material is abundantly present in the earth. So we can easily get this metal, and the cost effectiveness is very less. Thank you.